Yeah, there's both extremes for sure. All right, so what do we got? There's got to be questions. It is the 13th.
You had to do math today.
It's a little bit.
All right, keep it open for another second. Anybody got questions? Call them out now. Okay. Well, let's move on. So, hopefully that handout was helpful about the different functions to try and use to start with for the finding a particular solution. So the particular function of a non-homogeneous equation, right? Have those starting points and things to look for when we're doing the method of undetermined coefficients.
So, like for our next exam, are we gonna? Will you have that sheet, or is this a sheet like
I might provide that sheet for you just so that you can save some room on your note sheet. You know what I mean?
What color is it? The blue or white?
White.
Oh, man.
Which one are we talking about?
No, blue or yellow. Yeah, those are the ones I generally send out and say, oh, you can use this on anything. But I'll probably allow you to use that or put it up on the overhead during the exam or something like that. Okay. All right. So yeah, at some point there's just a whole lot of stuff to remember, right? So that's the thing. You got to realize that you can't possibly memorize everything you see in here. So some resources you have with you, some, you do enough repetition to get used to the process. Some things, the process is too long, and yeah, there are those results like variation of parameters where you have that written down, okay? All right, so let's get started then. All right, so we are going to be shifting towards simultaneous systems, a system of differential equations, like a system of linear equations and two unknowns or something. But we're going to move into systems of differential equations. And the next couple examples are just going to be sort of motivators for that. Okay, so we're going to see system, where do they come from potentially. And then the several sections after that is devoted to methods of solving them, okay, including getting up to speed on some more linear algebra techniques, things like that. All right. So, we got a brine solution again, one of these mixture problems. So 2 tanks of brine are connected as shown below, right there. This is just the same diagram, I just cribbed it from the book. So you got 2 tanks, tank 1, tank 2. Tank 1 contains X of T, pounds of salt, and it's 100 gallons of brine in there. Tank 2, we're calling the amount of salt Y of T. So, and that's in pounds as well. And that's in 200 gallons of the brine solution, so there's more in there, twice as much. The brine in each tank is kept at uniform concentration, so that's a big assumption, but we're going to assume it by somehow stirring, and it simultaneously becomes homogeneously stirred up, right? So, or at least in each one. So in each tank it's homogeneous. And by homogeneous, I'm not talking about the differential equation type of homogeneous, I mean concentration is constant. Okay. Now a couple little things here. So there's fresh water coming into tank 1, being pumped in at 20 gallons per minute. That's fresh water, so no salt. Tank 2 is feeding into tank 1, right? Or tank 1 pumps into tank 2, so down here at 30 gallons a minute. Tank 2 in turn pumps into tank 1 at a rate of 10 gallons per minute. All right, and then tank 2 is being emptied at a constant rate of 20 gallons per minute out. So that stuff is going to be a variable solution, variable concentration. So one thing to convince yourselves of is that is the amount of solution in any of these, in either of these containers going to be changing? All right, so we got 20 gallons a minute in, 10 gallons a minute in, so overall 30 gallons a minute entering, 30 gallons a minute exiting. Okay, so that's constant volume. Over here we got 10 gallons exiting, 20 or 10 gallons per minute, 20 gallons per minute, so 30 gallons per minute exiting, 30 coming in. So net change in volume, 0. And notice that 20 gallons a minute in, 20 gallons a minute out. So yeah, so there's the same amount of, there's a lot of ins and outs to those two tanks, but overall they're not changing volume. Of course, it is going to be changing concentration, so the amount of salt in there, because we're pumping in fresh and out goes that salt. So overall it's going to be diluting.
What kind of process is this?
I don't know. It's a cooked up process. They say, suppose that there's some fermentation vats that are doing this, pump from one to the other and back and forth and things like that. I don't know if it's ever done.
Like, I don't know, maybe like a water system at like a pool.
Oh, a desalinization plant or a water treatment facility. And this is our drinking water or something. You wanted to go through a lot of purification processes.
Wait. Students in math class, and they're responsible for our drinking water?
Oh, right. That's an engineering thing. My dad did some work on the sewage treatment plants. Engineering end, not the hands-on end. Anyway, so what we're going to be doing is looking for a system of equations that models this situation. So a differential equation for x of t and one for y of t. So let's start on that path here. So for x of t, let's talk about tank 1. Tank 1 first. And the change, dx dt, and it's going to be measured in pounds of salt, and t is measured in minutes. So that's going to be pounds per minute, rate of change. Always start the same way, rate in minus rate out. And we just got a couple of different inlets here. All right, so let's talk about the rate in. We got 20 gallons per minute. Uh, 20 gallons per minute coming in, and I like to put the units in there, highlight them. Right, gallons per minute. And what's the concentration of that stuff? 0. And 0 pounds of salt, right, per gallon. All right, we got another one coming in, so I'm adding that. Okay, plus we got 10 gallons a minute. And what would be the concentration of this?
Y sub t divided by 200.
Right, we got that many pounds of salt. Y or y of t, y sub t, or y of t, over 200. And that's measured in pounds per gallon. All right, that's the rate in. And then the rate out, it's going out at 30 gallons a minute. And times, what's the concentration of the stuff that's leaving? It's variable concentration.
So t divided by 100.
X pounds per 100 gallons. So this is a lot like the stuff that we did earlier. Okay, so familiarity, gotta love it. Now, the units, just a little analysis, gallons. So we have pounds per minute of salt. Of course, here we got just a 0. Here, gallons, so I got pounds per minute of salt coming in, minus, and the gallons cancels out. I'm going to have pounds per minute exiting. So we got a 0 there, and 10y over 200 is going to be the same as what? 1y over, or y over 20? Minus 30x over 100, so the factors of 10 will cancel out, 3x over 10. Okay? And we can write this as x prime, right? As long as we know that prime refers to t. That's one, again, you know, Leibniz notation has one big advantage, and that's that it's clear what the independent variable is, but primes equals derivative with respect to t here. Okay. All right, so that's tank 1. Let's do the same thing for tank 2 here. So same sort of analysis, and this case, we're calling it Y, right? So the change in volume of salt, or weight of salt. dy dt, rate in minus rate out. All right, so tank 2, what's coming into it? We got that 30, whereas that was flowing out of tank 1, so that was in the out business. Now it's flowing into tank 2, but we got, and that's a positive 30. All right, is that better? Okay. All right, so we got a 30, and that's gallons per minute. And we already know about the concentration of that. Oops. Yeah, coming in at X over 100 pounds per gallon. Okay, so that's the in, and what about the out? Right. 10, and can I ditch the units for a moment now? Imagine that the units are here. And what other one?
Times y over 200.
Oh, right.
Yeah.
10 times y over 200. Okay. And another one coming out, 20, and that's gallons per minute of concentration, y over 200. Okay. So, yeah, gallons cancels with counts. We're talking about a rate in terms of pounds per minute. So this will be 3 over 10 again, 3x over 10, I should say, minus the factors of 10 will cancel. I got y over 10 minus, what's that?
Wait, that's one over 20. Why don't you combine them, or can you combine them?
Yeah, you could. Yeah, you can combine them now or in the next step. Well, this one was the minus 10 y over 200, right? Yeah. And minus 20 times y of t over 200 as well. So the 10s we cancel out, that's 1 over 20. Oh, right. 10 y over 200 minus 20 y over 200 minus 3 y over 200, or 30 y over 200, so that's going to be 3 y over 20. Is that right? Yeah. And that is y prime. Okay. One thing I'm going to do with these is just clear the fractions. So multiply both sides of this equation by 20. You'd have 20x prime equals y minus what? 6x? Top one. Multiply both sides by 20 to clear those fractions. 60 over 10, yeah. All right. And we could do the same thing over, oh, there's another y. I could combine these two, right? Equal 3x over 10, y over 20 minus y over 10 minus y over 20. These are still kind of like terms. These are y terms.
We can't see what you're talking about.
There we go. This guy right here.
Yeah.
So I had 3x over 10 minus y over 20 minus...
That's what I was saying, combine it.
Hold on.
They had the same
Now I'm
denominator
getting
last term.
Okay, so 3x over 10, you can combine it here. That would be minus 10y over 200, 20y over 200. That's 30y over 200. 30. That's why I brought in the pencil and the eraser today. 30y over 200, or 3x over 10 minus 3y over 20. Good. Now, if we clear the fractions on this one, multiply both sides by 20 again, we'd have 20y prime equals 6x minus 3y. Okay, so call this one for tank 1, that's equation 1. This equation here for tank 2, they're obviously related. They both contain the variables y and x, the those unknown functions. So these equations are tied up together. So in other words, this forms a system. equations 1 and 2 yields a system of differential equations. So we got 20x prime equals y minus 6x, and the other equation right here, 20y prime equals 6x minus 3y. Okay, so this is a system of differential equations. All right, so any question about how they were derived? It was not too bad, not too bad. Very similar to what we did in the previous chapter, okay? But now, x and y, the solution of a system, well, a solution of a single differential equation would be a solution for the function x that satisfies this, right? Okay, so the function x of t. But taken together, the solution is a pair of functions, x of t and y of t, that satisfy both equations. Okay. All right. So we're not going to solve that right now. Okay. We're going to be building up the methods for that. But just so you can see that, yeah, we do have a system of equations, differential equations. So this is section 4.1 in the book. So we're going to be doing like a little bit of an introduction. Systems of differential equations, an intro. Okay, so we saw that that one could be derived there. All right. So, just a little bit, terminology. When we talk about solving a system, to this system or any system of differential equations, is not just one, but a pair, in this case, two equations, two unknown dependent variables. So it's a pair of functions. X of t and y of t that satisfy not just one, but both equations. All right, so any questions so far? Kind of like two linear equations in two unknowns, if they're just real numbers, x and y. They were searching for those pair, x and y, of unknowns. Here, our unknowns are not constants, they're functions, right? A pair of them, x of t, y of t. Okay, so other systems may arise from, different things. Circuits is one place, but it's not one that we looked at, but circuits, electrical circuits. But two-mass system. So a mechanical system containing two masses on springs. So out of the wall, here's one spring connected to mass 1. Connected to another spring, and mass 2. All right. So again, if we call x the equilibrium position of the first, y the equilibrium position of the second, and I'm just going to write this down. This is not to memorize, but just to show you where equations or system of equations could rise from. They do talk about this in the book, but m1x double prime equals negative k1x plus k2 times the difference, the distance between y and x, or their displacement. m2x double prime, very similar, negative k sub 2 y minus x plus, and if there's some external force, if this is connected and there's some other external force being applied on this, this is what we skipped in 3.6, but if there's some sort of external forcing function. We can solve them now if we have a non-homogeneous, if we have a forcing function on a linear differential equation, any order. Now with our methods of undetermined coefficients and variation of parameters, we could solve those if there's an external force being applied. Another example, a predator-prey system. So if you have a simple population model of two competing populations, like whatever, rabbits and foxes or something like this, right? They're related to each other if they're sharing the same environment, because one is a prey, one's a predator, right? The more there are of the rabbits, the foxes have more to eat. They can sustain a larger population until the point where there's so many of them that they deplete the population of rabbits. And cyclical in theory, okay? So another example, predator-prey. So say x prime, this is the population rate, rate of population change. Okay, so there would be a system that models it where x represents the number of rabbits. 2B's, rabbits, and y represents the number of foxes.
Death rate is proportional to the number of foxes, essentially.
Right here?
Yeah, because wouldn't that be like birds and deaths?
That fits it. I think it's section 2.1 is where we looked at some population models. We looked at tweaking the birth rate and death rate a little bit. Yeah. So the larger y is, the more negative x prime is. Yeah, that's something you can see there. And that's something that's in future chapters. Okay. All right. So this section, like I said, is just an intro. Let's look at an example. Some things we can do, and this doesn't require any linear algebra, but converting a single nth order equation into a system of differential equations. Okay, so sometimes we can do that. So just as an example, consider this equation third degree 2y third derivative, so y triple prime, minus 3y double prime, plus 5y prime, minus 6y, equals 2 sine 5t, or something like that. Okay. So this is what we were talking about before. This would be non-homogeneous. This one would be our function f of t, the non-homogeneous bit. Okay. So what would be our strategy at this point? So now, how would we do this? Find the
Characteristic equation of the homogeneous whatnot.
So if I drop this part, let it equal to 0, we could find the complementary function. That's the general solution to the homogeneous, so to the homogeneous equation. So we find the complementary solution. Oh, some things about it, yeah. It is linear. This one has constant coefficients. And it is non-homogeneous. Okay. So at this point, what we would do, our normal strategy is we could find the complementary solution, y sub c, right? Assuming that y takes on the form e to the rx, right? And we could find the values of r. Then, with the methods that we looked at last time, homogeneous or undetermined coefficients, possibly variation of parameters, we could search for a particular solution. What would we try, probably, for the particular solution? Just a little bit of review. Right, yeah. So, form of f of t, yeah, would be some constant multiple sine 5t, but iterations of differentiating it, we get a cosine 5t constant multiple. After that, they'd start repeating sine 5t, cosine 5t.
Sine 5t.
So something that captures both of those forms.
A and B.
Right. So, and we can deal with any constant multiple. Those will be solved in A and B. So we would try probably A sine 5t plus B cosine 5t or something like that. Okay. Depending on what we get for the complementary solution. If the complementary solution, remember, contains those, that's when we have a problem. Okay. All right. And then the general solution, y, and is this, it's t. Then y of t would be complementary solution plus the particular solution. Okay. All right. Another approach, we could sort of resolve this into a system of differential equations. Okay. So let's make a series of assignments. Okay. So just for y, we call it y sub 1. Okay. And y sub 2, I'm just going to go over and call that, let that be y prime for a second. But what you might notice is that y prime is the same thing as y1 prime. Okay. And y3, I'll let that be y double prime. So we're capturing all these derivatives. But y double prime is just y2 prime. Right? All right. So look at its derivative, then y3 prime is y triple prime. Right? y3 prime would be y triple prime. Now, if I solve this isolated y triple prime there, what would it look like? I'm going to get everything over to the other side, solve for y triple prime. I'd start off with 2 sine 5t plus 6y minus 5y prime plus 3y double prime. Okay? And then I'd have to divide it by 2 because I want to get y triple prime by itself. So now with 1/2 out front of all that. Now what I'm going to do is replace all these y's and y primes with their, over here, this assignment that we had. So y triple prime would be 1/2, and I'm going to move this out to the end. whatever, we'll keep it there for now. 2 sine 5t